Hello, everyone. This recitation is about PyTorch tensors and what are the most used operations that we perform on PyTorch tensors. So the contents are basically an introduction about PyTorch tensors, how do we create them, how do we access and modify those tensors, and how do we pivot and reshape the tensors. Let's move ahead. So PyTorch is basically an open source deep learning framework, and it provides us with building blocks to implement, train, and test deep learning network very easily. And PyTorch is very, very widely used in the industry, and it's used almost, in many, many, many companies, right? So to install PyTorch, we could use many package installers, but in this particular recitation, we'll be using pip, and here's how you can install pip. Install Torch, Torch Vision, and Torch Audio. So I have run this cells and all these in this particular notebook to ensure that we have the output from beforehand. But yeah, once you install this, you could use it and create tensors and work with them. So let's move ahead and see what are PyTorch tensors. So tensors are basically a specialized data structure and which are very similar to arrays and matrices. And PyTorch tensors are used to encode inputs, outputs, and all the other model parameters when we are working with PyTorch tensors. So PyTorch tensors can be of varying dimensions. So it can be a scalar, it can be a vector, it can be a matrix, or it can be of a bigger dimension or any other n dimension tensor. This looks quite similar to how we work with NumPy arrays. So what's so different about NumPy arrays and say the tensors? So the difference is that the tensors can be run on GPUs or any other hardware accelerators. So we could parallelize the tensor computation, and this will help us reduce the runtime very, very drastically. So let's get ahead and see how we can create tensors. So for that, first we'll import Torch as follows, right? And then one thing to note here is that in the environment, in the runtime that we are at, we need to first check that is this runtime compatible? Does this have GPU or does this just support a CPU? To check that, we could run this command torch.cuda is available, and we can see here that it prints a false here. So if you're working with Google Colab, we could change the runtime by going here in the runtime option and then change runtime, and then we could select the hardware accelerator we need. So currently set to none, meaning we would have just access to a CPU in this runtime environment, but we could choose a GPU or a TPU as well. For the purpose of this recitation, we would just continue with CPUs, using CPUs. Let's see how we can create a tensor. So to create a tensor with all ones of shape 5 cross 3, we could just use torch.ones and we would get a tensor of this kind. If we want to create a tensor of all zeros, we could use torch.zeros. To get an identity matrix of shape 3 cross 3, we could use torch.I. We could use torch.rand to create a random tensor of this particular shape. So basically, torch.rand would create a tensor which is uniformly distributed, and the values would be uniformly distributed between numbers 0 and 1. So here's the example for that. And the torch.arange is used to create basically a 1D tensor of integers with numbers varying from the range 0 to n minus 1. So here the numbers would vary basically from 0 to 6 in this case. Moving ahead, say if we have existing data in the form of lists or NumPy arrays, how can we convert them to tensors? So we could use torch.tensor and provide the list or the NumPy array and get the tensor out. Say we have an existing tensor and we want to create a copy of that, we could use the .clone method and create a copy of the existing tensor. Let's see another method to convert the NumPy array to tensor. So say we have a NumPy array here and we want to convert it to tensor. So other than using torch.tensor to create a tensor out of the NumPy using the NumPy array, we could also use torch.fromNumPy and pass the NumPy array and get a tensor. So here in this example, we see that we originally have a NumPy array, and all the elements of this NumPy array are of type int64. We converted this particular NumPy array to a tensor, and all elements are of now data type torch dot int64. So this is the PyTorch supported equivalence of int64. Now, if we want to change the data type of elements in this tensor, so to say float, we could do tensor.float, basically the tensor that we have dot float, and all the elements of the tensor will be now of data type float. Moving ahead, now see we have a tensor, and now we want to convert it back to NumPy array. So what do we do for that? So we have a tensor here, T1, which is basically this. And now we want to convert it back to NumPy. So we would use the dot detach method. Now we use detach to basically first detach the tensor from the computational graph and then convert it to NumPy array. So for more information about computational graph, you could go to this link, and I think it will be very helpful. So here we see that after doing this, we get a NumPy array here. Now we saw that in this particular runtime environment, we could support CPUs and GPUs, and tensors have the capability of basically being used in a runtime in an environment which is supporting CPUs, GPUs both. So say if our runtime environment actually supports GPU, how can we push the tensor to the to a GPU? So for that, what do we need to do is first we need to check if basically GPU is available or not. And if it is available, we set torch.device to CUDA. And how do we push this particular tensor to this device? We use tensor.toDevice, and then this particular tensor would be pushed to pushed to whichever device which is currently supported in this runtime environment. So in our case, currently we are working with CPU, so our tensor is in CPU itself. But if we had GPU in our runtime environment, this would reflect as GPU. You could try that out. You could change the runtime environment to GPU, and then this should basically come as GPU here. Now let's see how to access elements or rows, columns, or various parts of the various portions of the tensors, and how to modify the tensors. So the indexing in tensors works very, very similar to that in the NumPy arrays. So let's just first create a tensor of shape 3 cross 4 cross 5 as mentioned here. So this is our original tensor which we'll be working with. Now, if you want to index the 0, 0, 0th element, so what we how can do is t of 0, 0, 0, 0, and then that would basically fetch the item from the first dimension, first item from the first element from this first dimension, and pick the 0th row of this and pick the 0th element from here. So this is what is printed. We could also use this particular format and not give which is definitely more convenient, and this works too. If we want to say index elements from the back, from the not from the start but from the end, so we could also use -1 or -2 or -n to index basically the nth element or the nth row or the nth column. So here what we are doing is we are choosing this particular element, then we are choosing the last row, and then we are choosing the last element in the last column. So if we see here, t of -1 -1 -1 gives us this particular element here, right? So next, moving on to tensor slicing. Say we want to get the element at t of 0, the 0th element, which is basically the item in the first item in the first dimension. So this would basically fetch this particular section of the tensor. So for that, we could use t of 0. And one another part is, so say we want all elements from the first dimension, but only the first rows from the second dimension. So what we could do is we could use this particular notation, t of colon, to basically pick all the elements from the first dimension. We have all of this, and but from the first dimension we just want the first rows. So that means that we are interested only in this particular row, this particular row, and this particular row. So similarly, if we when we execute this, we see that the tensor now basically sliced to contain only the section, this particular section of the original tensor. So basically, you can try out all these slicing operations listed here and see for yourself that it's working as expected. Moving on, let's talk about pivoting and reshaping tensors. So the first operation that we'll talk about is flattening. So if we have, say, a tensor of shape 3 cross 4 cross 5, which is a 3D tensor, and we want to convert it to a 1D tensor, we could use the flatten function, and this would basically convert this 3 cross 4 cross 5 dimension 3D tensor to a 1D tensor. So if you see the shape of this flattened tensor, shape of this flattened tensor is now 60, right? So the number of elements always remain constant. So since it's 3 cross 4 cross 5, the number of total elements is 60. So that retains, that is retained, all the elements are retained. And while flattening, it's just a 1D tensor with 60 elements in it. Moving on, let's check out what is squeeze and unsqueeze. So squeeze and unsqueeze are used to basically add and remove a dimension from the tensor. So you can think about what's the use case of unsqueeze. So so you could use unsqueeze whenever you need an extra dimension, and this use case is basically comes up when we want to have extra dimension for, say, batch size, when we are working with deep learning models. So again, we had this original tensor of shape 3 cross 4 cross 5, and now say we intend to add another dimension, and so we could do something like t dot unsqueeze and add a dimension in front of basically the current 0th dimension, so dim 0 if we specify. Now what happens? Let's just let's just check the shape of the new tensor, right? So original tensor shape was 3 cross 4 cross 5, and after we added a dimension by using unsqueeze, we unsqueeze along axis 0, and now the tensor has the size 1 cross 3 cross 4 cross 5. So we added an extra dimension at the start. We could also add extra dimension at any other axis. So if we do t dot unsqueeze of 1, we end up adding we unsqueeze along axis 1, and now we see that the shape is 3 cross 1 cross 4 cross 5, and we have added the dimension at the first along the first axis 1, not axis 0, as in this particular case. Yeah. So similarly, if we have the support of unsqueezing and adding a dimension, PyTorch also allows us to squeeze and remove dimensions. So we could just say ts.squeeze and give the dimension from where we want to remove the extra axis. So say originally, in this example, we are using ts. So here ts basically refers to this particular tensor where the dimension is 1 cross 3 cross 4 cross 5. And if we do a ts dot squeeze of the axis 0, we basically get what was the shape of the original tensor. So after ts dot squeeze of 0, we get the torch we get the tensor of size 3 cross 4 cross 5. Moving on, let's see what happens, how we can use a reshape function. So say in the original particular tensor now, which was of shape 3 cross 4 cross 5, we want to reshape it so that we have only 2 dimensions. So how do we do it? So what we could do is we could give t dot reshape and give uh, uh, we could specify um, uh, we could specify the dimensions here, right? So here we have 12 cross 5. So that's what we see. This particular tensor of shape 3 cross 4 cross 5 is now reshaped to 12 cross 5. Other ways, other way is you always do not need to specify both of these 12 and 5. It is implicit that the number of elements in the original tensor remains intact. So if say 3 cross 4 cross 5 translates to having 60 elements, if we specify 12 in the 0th in the first dimension and specify -1, it just would infer that this should be 5. Right, so that is equivalent to just specifying 12 cross 5 or 12 cross -1. View, the view functionality is very similar to reshape, and but it is a little tricky in and might not work exactly like reshape all the time. But to if you're curious and want to know the differences between reshape and view, you could basically go to this link, and gives a very good example uh, explanation. Now let's see that what's the use case of transpose. So transpose operation is basically a generalization of our regular matrix transpose. So again, here, if we have a tensor which is of shape 2 cross 3 cross 4, if we want to transpose 0th and the first axis, so let's see how it works, right? So original size was 2 cross 3 cross 4. After transposing the 0th and the first axis, we see that the size is now 3 cross 2 cross 4. We could also transpose not just consecutive axis, we could also transpose 0 with the second axis. So in that case, we see that 2 cross 3 cross 4 is now converted to 4 cross 3 cross 2. Now permute is a more generalization of um, what we saw here, and it gives us to permute multiple dimensions at once. So it's a much more generalized version. And we could simultaneously reorder multiple dimensions, unlike transpose, in which we could just interchange 2 dimensions at once. So here again, the original tensor is of shape 2 cross 3 cross 4. And if we do t dot permute 1, 0, 2, what it does is basically it permutes the 0th dimension with the first dimension with the 0th dimension, and it keeps the second dimension intact. So let's see what it does. So it permuted, so in this example, it permuted the 0th dimension with the first dimension. So 2 became 3 and 3 became 2 here, right? It got permuted and the second remained intact. In this particular example, if we do a permute, t dot permute 1, comma 2, comma 0, it basically means that we are changing the 0th dimension to first dimension. First dimension with, we are reordering the first dimension with second dimension, and the second dimension with 0th dimension. So if you see here, what happened here is the 0th dimension here is reordered with the first dimension of the original. The first dimension is reordered with the second dimension of the original, and the last dimension is reordered with the 0th dimension of the original. So torch.permute is basically widely used, very, very widely used, and you will be using it in yeah, many assignments basically. And it allows us to basically do multiple reordering of the dimensions simultaneously. Um, yeah, this is the first part of the 0D recitation. There is another part to it, which would basically talk about other operations that we could do with the tensors. And please watch that as well, because it covers multiple other operations which will be widely used widely used in this course. And all the best, and thank you.